You're welcome to Excellent Simplified Tutorials.
Now, we are going to look at abnormalities and disorders of nucleic acid metabolism. Can we say that? How to know people that went to nursery school and people that did not go to nursery school. Now, the abnormalities or disorders of nucleic acid metabolism. You know, metabolism now we are talking about the synthesis and the breakdown, is it not? Anabolism and catabolism. So we are going to look at disorders associated with those pathways. And most of these disorders are usually enzymopathies. Disorders associated with the enzymes. Now, not all by the way. So we are going to look at some of them here. We have 7. The first one here is what? Xeroderma what? Pigmentosum. Now look at this. 0. What are xerophytes? Plants that live where? On dry land, right? Xerophytes, is it not? Now, when we say 0, 0 means dry. 0 means dry. And when they are talking about derma, derma means what? Skin, right? So xeroderma means what? Dry skin. Xeroderma means dry skin. Now, pigmentosum. Pigmentosum is also called what? Pigmentation, right? But this is not English. So when we say Xeroderma pigmentosum, people with this condition have what? Dry skin. And when they are exposed to sunlight, what do you see? Is that color change? Is it not? So pigmentosum is talking about color change, right? While Xeroderma is talking about what? Dry skin. Good. Now, Xeroderma pigmentosum occurs as a result of mutation. Mutation in genes involved in DNA repair. Are we together? So we said Xeroderma pigmentation occurs as a result of what? Mutation of genes involving what? Genes involving what? DNA repair. Now the truth is, as we are exposed to sunlight, ultraviolet rays from the sun can cause mutation, can cause DNA damage. But our body have a natural mechanism of taking care of those damages. Do you understand? Yes. So the body can actually repair those damages before any problem will occur. But in people with Xeroderma pigmentation, the gene that is supposed to facilitate that repair is mutated, is damaged, is not there. Do you get? So any damage in the DNA cannot be repaired. Do you understand? So people exposed to, when they are exposed to sunlight or ultraviolet rays from the sun, can cause DNA damage. And since the gene involved in the repair is not there, it will cause a serious problem. And so they will have 0, dry skin. Just like we say 0 is dry and derma is skin. You have dry skin and their skin will be pigmented. Do you understand that? So that is Xeroderma pigmentation. Now, biochemistry exam is not like any other exam. You must put what is responsible. If it is an enzyme, you must put the enzyme. Now, in this case, what is responsible for this disease? Mutation of what gene? Genes involved in what? There's what we call excision repair, DNA excision repair. Excision repair mechanism. This is the mechanism DNA use to repair damaged bases. But in this case, that cannot happen. Any question on this? Can we move on? All right. Yes. From where? What is 0? What is derma? So Xeroderma is what? Dry skin. So we said people with Xeroderma pigmentation, there is a gene normally, as you're sitting down here, there is a gene that is involved in DNA repair, right? But people with Xeroderma pigmentation, that gene is mutated. And so it cannot carry out that function of repairing the DNA. Do you get? It is normal for DNA damage to occur. It is normal. Because we are exposed to ultraviolet rays every day. So it is normal for DNA damage to occur. But our body have a natural mechanism to repair that damage called DNA excision repair. But in this case here, Xeroderma pigmentation, the gene involved in that repair is damaged. And so any damage now, the body cannot repair it. And so it will cause a big problem. Now, infants with this disease, once they are exposed to sunlight for around 2 minutes, you see pigments everywhere on their skin. Have it happened to you? Okay, then you have Xeroderma. Okay, no. All right. So this. Okay, very good question. Now from the cause, because before you can talk about the cure, you know what causes it. What causes this? Mutation, right? Can we cure mutation? Okay, say yes. Okay, we are in a modern world. We have what we call gene therapy now, which you can, sickle cell anemia is mutation, right? Yeah. Mutation of just one base. It's a point mutation that causes that. Valine is now changed to what? Glutamic acid is changed to valine. Just one amino acid changing, and it causes that. So they have gene therapy. Gene therapy, they can actually use gene therapy to do that, but not be child's play. Do you get? Good. All right. So the second one is gout. Now we said the end product of the breakdown of purine is what? Uric acid, right? Carbon dioxide in your mouth. Uric acid, right? Good. Now uric acid is the end product of purine breakdown, right? Good. Now this uric acid, is it sparingly soluble or very soluble? Sparingly soluble, right? So it can accumulate. Now what do you think can cause the accumulation of uric acid? When what? Now this is purine. If there is excess breakdown of purine, what do you think will happen? More uric acid will produce, right? And since it is not easily excreted, they will accumulate. Is it not? So excess breakdown of purine can lead to accumulation of uric acid, which is our gout. I would say gout is what? Painful what? Arthritis. Now some persons, if you want to know people with gout, just check their big toe. It is always swollen, inflamed. They check your own. Alright, so that's that. Apart from excess breakdown of purine, what else can cause gout? From your general understanding of what we've talked about, what else can cause the accumulation of uric acid? If you get it, plus 5 marks. You said? Breakdown of pyrimidine. Breakdown of pyrimidine. If we break down pyrimidine, what's the product? Carbon dioxide, water, and urea. So that does not affect this. Overproduction of what? Uric acid. But this is how it's produced now, by overproduction of this. What if it is not excreted? Okay, when uric acids are produced, what's the fate of uric acid produced during purine breakdown? What can it be used to produce? Okay, uric acid is used to produce urine. I'm learning new things in this class. Alright, uric acid can undergo oxidation. We'll look at that. Alright, but gout can be divided into two. We have primary gout and what? And what's the difference between primary gout and secondary gout? Sir? Okay, so the one that's actually wrong, but the one we've been talking about since is primary gout. Primary gout results from overproduction of purine. And if purines are overproduced, as they are overproduced, the breakdown will increase also, right? And so uric acid will accumulate. That is primary gout. But secondary gout results from combination of diseases. And if any disease prevents the excretion of uric acid will accumulate, right? So accumulate. So primary gout is the one most persons experience. Secondary gout results from combination of diseases. Alright, any disease that can prevent the excretion of uric acid. We know it's not very soluble. It's not that it cannot be excreted at all, but we said it's sparingly soluble. It can still be excreted, but not as urea. Urea is very soluble. It can be transported to the kidney, and one way is out from the body. But this one, it takes time. So when it is in high concentration, anything that makes it accumulate, in fact, some diet, some food, increase the production. Do you know that there are some foods that have more purines? Mention one. Do you know even your liver? If you eat liver, it has more purines. Beans have 2. Meat, most meats. So people with this condition, they advise them to manage their food. The food they eat, you don't eat foods with high purine contents. Yes, like beans, meat, liver, kidney, even some vegetables. You just fast. All right. Number, you'll see this thing tomorrow. You'll see it live tomorrow. Number 3 is what? Lesch-Nyhan syndrome. This is a combination of the two persons that discovered this. Lesch-Nyhan syndrome. Sir? What is acute gout attack? The treatment we said you should abstain from what? I mentioned several there. I gave you like how many? The first one I gave you was the what? Non-steroidal anti-inflammatory drugs like what? Ibuprofen, diclofenac sodium. All those drugs they advise ulcer patients not to take. Non-steroidal anti-inflammatory drugs. This is one cause of ulcer. We have 2 causes of ulcer. The main cause is what? Helicobacter pylori, right? And non-steroidal anti-inflammatory drugs. Pepper does not cause ulcer. Good. All right. So the next one was what? Say? Call what? Cortisone. The next one was what? Corticosteroids, right? Now in your BCH 414, you study this. And yes, they are most of them are steroid hormones derived from cholesterol. So till then. But for now, just know that these are involved. Next one there is what? Allopurinol. We already know allopurinol that it inhibits what enzyme? Xanthine oxidase, right? And xanthine oxidase is the last enzyme in the breakdown of purine. Is it not? So allopurinol is a chemotherapeutic agent that is used to prevent that last step. What's the last step? Conversion of what to what? Hypoxanthine to what? Xanthine to hypoxanthine to xanthine, and xanthine to what? Uric acid. It's the same enzyme catalyzing both reactions. Now, if that enzyme is inhibited, it means xanthine cannot be converted to uric acid again, right? And so uric acid cannot accumulate. Gout cannot occur because uric acid is not accumulating. Do you understand that? Good. Next one there was what? Abstinence from alcohol. For those of you, brother hearing, abstinence from alcohol. Excessive, I didn't mention your name, please. Excessive intake of alcohol will lead to what? The urate level, your uric acid level in the serum will be high. And that's what we are trying to avoid in case of gout. You know you have gout, you're taking alcohol. It will increase the urate level, the serum urate level in your blood, in your serum. And that can even complicate the issue. The next one there is what? Dietary modification. I've mentioned some foods you should not take. Foods rich in purines and others. Alright, because of our time, Lesch-Nyhan syndrome. Now, before I talk about this, remember how many pathways do we use in the synthesis of purines? How many pathways? 2, right? De novo synthesis and what? Salvage pathway. And you recall with me that in the salvage pathway, okay, if we have adenine in the salvage pathway, adenosine monophosphate, what is coming in? What is PROPP? Phosphoribosine pyrophosphate, and leaving as what? Pyrophosphate, right? Good. So we will now have adenosine monophosphate. And what's the name of the enzyme catalyzing this reaction? Adenosine what? Adenosine. Hey, relax. Relax. So after last class, These are points of interest here. From guanine to GMP, still PROP coming in, right? Leaving as pi. What's the name of the enzyme catalyzing this reaction? Rush it like that tomorrow. Now when you see the paper now, you keep quiet. Now, HPGROT, hypoxanthine guanine phosphorybosis transferase, catalyzes the reaction. If we look at the next one, hypoxanthine, the same enzyme, right? Good. Now, if this enzyme, remember, this enzyme catalyzes the conversion of free purine base to what? To the nucleotide, right? Good. Now, if this enzyme is deficient, what do you think? This base will accumulate and will be deficient of what? Good. In Lesch-Nyhan syndrome, this enzyme is deficient. Hypoxanthine guanine phosphorybosis transferase is deficient. And so since it is deficient, free bases cannot be converted to what? To nucleotide, right? Two things can happen. Who can tell me the two things? One, if accumulation of what? Free bases, right? Good. Now, if free bases accumulates, what do you think will happen? It can lead to gout, but how? Production of uric acid, how? This thing will accumulate in high concentration, and so they will be broken down, right? They will be broken down, and the end product of purine breakdown is what? So Lesch-Nyhan syndrome can also lead to gout. Is it not? Can lead to gout. Who have this one? I will seize this one. All right, so this, do you understand this? Another thing that can happen is what? Don't you think that phosphorybosine pyrophosphate will also accumulate? And if phosphorybosine pyrophosphate accumulates, it will lead to increased synthesis of nucleotides, right? Through the de novo pathway. Remember, the first step in de novo synthesis of purine is what? Ribosyl phosphate will be converted to what? Phosphorybosine pyrophosphate. Then the phosphorybosine pyrophosphate, next step is what? So glycine comes into form what? Sorry, glutamine comes into form what? Phosphorybosine amine, right? Good, that's the committed step, the rate limiting step. Now, if this is accumulated here, it will increase the synthesis of purine de novo. And so, increase in purine synthesis de novo will lead to excessive breakdown of purine also. Is it not? Uric acid will still be formed. Gout. Do you understand that? That is the Lesch-Nyhan syndrome. Now, problem I have with you is, all these things, don't economize your writing. They say write on Lesch-Nyhan syndrome. All these things you know, put it down on paper. They will not mark your mind. I wrote it on the tables of my heart. No, this one, write it down. Next question. The next disorder there is severe combined what? Immunodeficiency. Immunodeficiency. It's talking about the immune system, right? Good. The immune system. Good. Now, severe combined immunodeficiency results from the deficiency of what enzyme? Adenosine deaminase. And you agree with me that adenosine deaminase is the enzyme involved in the conversion of what to what? Adenosine to what? Inosine. Remember, if you remove what? Amino group from adenine, you get what? What is the base in inosine? Hypoxanthine, right? Now, adenosine deaminase is involved in the conversion of adenosine to what? Inosine, in the catabolism of what? Adenosine. Remember, AMP in the catabolism is converted to what? It can be first converted to inosine, or it can be first converted to what? Adenosine monophosphate. Then adenosine deaminase can now convert the adenosine to what? To inosine, right? Good. But if this adenosine deaminase is absent or is deficient, what will happen? Adenosine cannot be converted to what? Inosine. And so that purine cannot be broken down. Do you understand? And so the purine will accumulate. It can also lead to gout, but the combined deficiency here, the combined effects here leads to decrease or inhibition of the synthesis of what? Inhibition of the synthesis of what? DNA. DNA, because nucleotide is the building block of DNA, nucleic acid. Good. Hypouricemia. Hypo means what? Low, right? Anytime you see mia is what? Blood, right? So this uric acid, right? Hypouricemia. Low uric acid in the blood. Now, this is not actually a defect on its own, but if the uric acid level in the blood is lower than normal, is below normal, you know, uric acid cannot be easily excreted. It's sparingly soluble. So, if the level is low, it's a sign of underlying disease. Not a disease itself, but it's a sign of underlying disease. And it has no clinical significance. It has no clinical significance. But it's a sign something must be wrong. Something might be wrong. What do you think can lead to hypouricemia? SS? Hypo. Decrease what? Decrease uric acid production, right? That is decrease breakdown of purine. Another thing is decrease reabsorption. Remember, when we talked about the kidney, one function of the kidney is urine formation, right? Good. Now, the first stage of urine formation is what? Ultrafiltration, right? From ultrafiltration, the next stage is what? Selective reabsorption, right? Good. Now, substances, remember, in the ultrafiltration phase, as the blood moves with high pressure through the glomerulus, any molecule less than how many what? Let me see remembering. Less than what? Less than what? All of you take a sheet of paper, write your name and mat number. It's a lie. So you've all forgotten 312. Now, smaller molecules can be able to pass through the pores, the holes of the glomerulus, right? Molecules that the body still needs. Now, but in the second stage, which is selective reabsorption, those molecules are reabsorbed from the tubules back into the bloodstream, right? Now, if there is low renal tubular reabsorption of uric acid, meaning most of them are carried out with urine and it's not reabsorbed into the blood, we have low in the blood, right? That is one cause of hypouricemia. That's one cause of hypouricemia. Now, the next thing there is orotic aciduria. Orotic aciduria can be seen. Orotic acid is found where? What pathway did you see orotic acid? Pyrimidine synthesis, right? Now, in pyrimidine synthesis, we started with amino group from what? From glutamine, right? Combines with bicarbonate. So form what? Carbamoyl phosphate. Catalyzed by what? Carbamoyl phosphate synthesis 2, right? Good. Now, carbamoyl phosphate was converted to what? So, carbamoyl aspartate came in and is converted to carbamoyl aspartate. Carbamoyl aspartate. Now, fumarate goes out and we form what? Dihydroorotic acid, right? Dihydroorotic acid is converted to what? Orotic acid. Orotic acid. Now, remember, okay, now from orotic acid, orotic acid to what? Uridine what? Monophosphate, right? The name of the enzyme catalyzing that reaction is what? The name of the enzyme catalyzing that reaction is what? Uridine monophosphate what? Synthase, right? Uridine monophosphate synthase. Good. Uridine monophosphate synthase. Now, if uridine monophosphate synthase is inhibited or is deficient, you agree with me that orotic acid cannot be converted to uridine monophosphate, is it not? Because the enzyme catalyzing that reaction is deficient. So orotic acid cannot be converted into UMP. And so what will happen? It will what? Accumulate, right? It will accumulate in the blood, causing the condition orotic aciduria. Since it accumulates, it will be excreted in the urine, urea, orotic acid in the urine. Orotic aciduria. Do you understand? Orotic acid in the urine, because this enzyme that is involved in the conversion of orotic acid to uridine monophosphate is deficient. And so it cannot be converted to this. And so this will accumulate and be excreted in the urine, causing the condition called what? Orotic aciduria. There's no what? What was going out? From carbamide aspartate to, okay, it was aspartate that donated. We saw three things, right? Sorry, fumarate was not going out. It was in purine synthesis that fumarate was going out. Now, in this case, sorry, look at this. Carbon, 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 nitrogen, carbon, nitrogen, carbon. This nitrogen 1, right? 2, 3, 4, 5, 6. Is it not? Carbon, nitrogen 1, carbon, gas and what? Gas and what? And what? Okay, are cows or aren't cows? Alright, so G was what? Glutamine, right? This was what? Aspartate. And this is CO2, right? CO2 was producing what carbon? CO2 for pyrimidine. Carbon 2. Glutamine was producing what? Nitrogen 3, right? And nitrogen 1, carbon 6, carbon 5, and carbon 4 was what? Aspartate. So aspartate was not living as fumarate. Take note of that. So it was still there. Alright, good. So in orotic aciduria, we said it's a rare autosomal recessive disorder, right? Which one did we say is X-linked? Which disease is X-linked? Okay, we said Lesch-Nyhan syndrome is X-linked, right? Do you know what that means? It's linked to the X chromosome, right? And X chromosome. What's the karyotype for male? Male human beings. What's our karyotype? For males, right? Males. XY. The karyotype for female is what? XX. And they are saying it boldly. Alright, so XX for female, XY for male, right? So you agree with me that the females contain only what? Only X, right? They can never have what? Y in their lifetime. Good. Don't want to have it. You cannot have it. Alright, so now, if the man donates X and the wife donates X, which is the only thing she can donate, the child will be a what? The child will be a what? Is it a girl or a lady? Alright, a girl, right? Good. Now, if the man donates Y and the wife donates the only thing she has, it's what? The child will be a what? A boy, right? Good. So who determines the sex of a child now? The male, right? Good. Now look at this. When we say X-linked disease, meaning the disease is linked to what chromosome? X chromosome. And look at this. Look at the males. Who do we inherit our X chromosome from? We inherit the X chromosome from the mother. From the mother. So meaning that X-linked diseases are inherited from the mother. So they are only carriers of the disease. They don't express it. Reyes syndrome. Reyes syndrome. We said Reyes syndrome is called secondary what? Orotic aciduria. It's called secondary orotic aciduria. And we already know that orotic aciduria is a condition where orotic acid accumulates, right? And is excreted in the urine due to the deficiency in that enzyme, uridine monophosphate synthase. Now, what causes this secondary orotic aciduria? Mitochondria. Remember that this pathway, urea pathway, the mitochondria is where this stuff takes place, right? Pyrimidine synthesis. Now, a part of it takes place in the mitochondria. Now, if the mitochondria is damaged, then that pathway cannot continue. What will happen to the carbamide phosphate? Will be channeled to what synthesis? The synthesis of what? I gave you the notes there now. Production of what? Read what you have there in your notes. Let me show you the writing.
Which might be diverted from.
Read from what? From the secondary orotic aciduria.
This is a secondary orotic aciduria, which may be due to inability of severely damaged metabolic to utilize for the way. Which then may be diverted from overproduction.
If you remember the pathway for urea formation and pyrimidine synthesis, they have the starting reaction is the same. Amino group from glutamine we combine with what? CO2 or bicarbonate, right? And we form what? Carbamoyl phosphate, right? Good. Carbamoyl phosphate. In both reactions, in synthesis of pyrimidine and synthesis of urea, this is the first reaction. But now, in urea pathway, what enzyme is catalyzing this? Carbamoyl phosphate synthetase what? 1, right? Why in the synthesis of pyrimidine, the enzyme is what? Carbamoyl phosphate synthetase 2. Is it not? Good. If the mitochondria is damaged, this carbamoyl phosphate here cannot continue in what pathway? In the synthesis of what? In the synthesis of what? Urea, right? So it will be diverted to the synthesis of what? Pyrimidine. Remember that in the breakdown of amino acids, if we break down amino acids, we have two parts, the amino group and the carbon skeleton, right? The carbon skeleton can be converted in the TCA cycle. The amino group, ammonia is very toxic to humans. Yes, ammonia is very toxic. And this breakdown takes place in the liver. Now your body will now say, this ammonia is very toxic. How do I take care of it? How do I handle it? Because if you allow it for some time, forget it, you are gone. Painful exit. Now, that ammonia will be converted in the liver to urea. This is the formula. This is urea now. This is urea. You can see that we have two amino group here, right? And a carbon at the middle. Now, this urea now is soluble, so it will be transported to the kidney and excreted, making that toxic ammonia less toxic. Is it not? Now, if the mitochondria is defective, what will happen is the carbamoyl phosphate cannot be channeled to the formation of what? Urea, right? And so it will follow what pathway? Pyrimidine synthesis. That's that. It's almost the same thing as orotic aciduria, but we call it secondary orotic aciduria. We know the difference, right? Here in orotic aciduria, what enzyme is deficient? Uridine monophosphate synthase, right? Why in Reyes syndrome, we say the mitochondria is defective. It's severely damaged. Any question on that? I'm done with the disorders. Alright, as we were saying before the tapping information came in. Now, central dogma of molecular biology. Are we together? Now, the central dogma of molecular biology, now take it this way. We want to synthesize protein. When we mention protein, don't only limit yourself to dietary proteins like the proteins you get from your meal. No. Because as I mentioned protein now, should I think of beans? Egg? No, it's not like that. Proteins can actually be synthesized in our system. Some hormones are proteins. All enzymes are what? All enzymes are proteins. So the protein we are talking about here can be an enzyme, can be hormone, can be anything that is hormone, that is protein made in our system. So the protein we want to synthesize now. We want to synthesize it. But the information we need, the resources we need to synthesize this protein is found on the DNA. Do you get? We want to synthesize protein, but the resources we need is found in the DNA. Now let's look at this cell. This is the nucleus, right? And this is where the genetic material is, the DNA is, right? Good. Where does protein synthesis take place? Protein synthesis takes place where? The ribosome, right? Good. Now the ribosome is found here, right? In the cytoplasm, right? Is it not? And the DNA is found in the nucleus. This is where the protein synthesis want to take place. And the ribosome found in the cytosol. But the information we need to synthesize this protein in the ribosome here is found in the nucleus. So we need to get into the nucleus, get the information, and use it to synthesize our protein. The process whereby information on the DNA is used to synthesize protein is our central dogma of molecular biology. And it's a one-way street. From DNA first, this DNA, I will go into the details, but get the overview. This DNA here is first converted into mRNA, messenger RNA. The messenger RNA leaves the nucleus now into the cytosol and gets on the ribosome now. Several things are happening, but on the ribosome, in the ribosome there, that's where the proteins are synthesized, is it not? Good. Now this is what is actually happening. Take it this way. You want to cook rice. The rice is our protein now. You want to cook rice, but you don't have rice in your house. The rice is in the market. What do? You first go to the market, right? Or send your messenger, your houseboy, to go to the market, buy the rice, get to the house, you give to your cook cooks. Then you do what? You eat. Now this is what is happening here. First, the process whereby DNA is converted to mRNA is called what? Transcription, right? Good. Now look at what is happening now. These are DNA. Let me take, let's say we have CGT. What will be here? G what? CA, right? Now what will happen is, a segment of this DNA will be taken. A segment of the DNA will be taken in form of what we call codon. Codon means triplet of bases. 3 bases combined. 3 nucleotide bases combined. So if we take this in form of codon, like if we have something like this, C, G, T, A, C, T. How many codons do we have here? 2, right? Because 3 bases will give us 1 codon. And each codon codes for a particular amino acid. But first, this DNA sequence, will be converted to mRNA. Will be converted to RNA. Now, you agree with me that, okay, if we want to take the complement of this, what will be here? G, right? C, A, C, G, A, right? If I want to convert this to RNA strand, here will still be G, here will still be C, here will still be A, here will be what? U, right? Instead of T, U, G, and A. Now, the DNA has been converted to RNA. That's the first thing that happens. The DNA here, the sequence of DNA is first transcribed into a molecule of mRNA. Now, the messenger RNA now leaves the nucleus and gets on the ribosome. You know, we have 3 types of RNA, right? Messenger RNA, transfer RNA, and what? And ribosomal RNA. Ribosomal RNA is there on the ribosome, assisting the process of protein synthesis. Good. Now, after the mRNA has been formed, the next thing is translation. Remember, the mRNA is coming with codons, right? Triplet of bases. And I said each base, each triplet of bases codes for a particular amino acid. You do that very well in this H415. If it's in my channel, if you want to know how you get the 64 codons, we have 64 codons. How you get it is right there in my channel with the acronym. How to remember how each amino acid codes, so each codon codes for amino acid. Go there and watch it out. Now, for example, UUU codes for the amino acid phenylalanine. UUU is a codon that codes for the amino acid phenylalanine. For example, again, GUC codes for leucine. Sorry, codes for valine. Codes for valine. Like that. We have 64 codons like that, coding for different amino acids. Now, each codon is recognized. The transfer RNA is involved in that. There's what we call an anticodon. The transfer RNA recognizes this and helps to transfer it to the right sequence. You do this in details later, but just get the overview. Now, in the ribosome now, the information, which is the codon, is used to synthesize individual amino acids. And individual amino acids will link together to form our what? Our protein. For now, just know that the central dogma of molecular biology involves this. DNA to mRNA is called what? Transcription. The process of converting DNA to mRNA, messenger RNA, is called transcription. Then the process of converting information in the messenger RNA to protein is called what? Translation. This is the central dogma of molecular biology. And it is a one-way street. You cannot go from mRNA to DNA when you want to synthesize protein. Though we have what we call reverse transcription. But if you want to synthesize protein, cannot go the other way around. You cannot go direct. For those of you that like shortcuts, you cannot go like that. Cannot go like that. Do you understand that? That's essential. I have a very strong, I don't know how do they call it, feeling that this thing will come tomorrow.